Hello everyone, today I'll be starting my lecture on nuclear physics, and this today will be the introduction to the rest of the unit for nuclear physics. So when Ernest Rutherford was doing his gold foil experiment to determine what the shape of an atom actually was, he was also simultaneously working on trying to identify the types of radiation that's emitted from atoms and from molecules and many unstable isotopes of atoms. So he built off of research that people like Marie Curie did in their lifetimes, and people at this time knew that yes, there was something called radiation being emitted from an atom, and that this most likely had to come from the core of an atom because it wasn't observed in anything like the electron shell or anything like that. And so when Ernest Rutherford was doing his experiments, he identified three main types of decays of atoms, so radioactive decay. And what he found was that there's alpha decay, beta decay, and gamma decay. So alpha and beta decay are not that harmful to humans, and they're not that penetrating either. What penetrating means is that it can go through substances, because we know radiation, it's going to be a type of particle / wave, and because the higher frequency a wave has, the more penetrative that wave is going to be. And so alpha decay, he found that it barely could pass through a sheet of paper. Beta decay could pass through 3 millimeters of aluminium, and gamma decay was actually really harmful because it could pass through multiple sheets of lead and keep going and going without anything stopping it. However, there is one question that arises, is how did Ernest Rutherford manage to even isolate these types of decays, and how did he find out what these types of decays were? Like, what was his methodology back 100 years ago, let's say? And so the main way he did that is using a magnetic field, which I'll illustrate next in the next diagram. So as we see in this diagram here, this is what Rutherford observed when he launched these particles into a magnetic field. And as we know, charged particles, they're going to be deflected in this magnetic field. So the first type he found was alpha decay, which he found to be positive in a magnetic field. If you use your hand rule and you see the magnetic field that's pointing out of the page, and you know the velocity of the particle, then you can determine what type of particle it is. So this one he determined to be positive. The gamma ray, he determined that it's going to be a neutral because it wasn't affected by the magnetic field at all. And the beta particle, he assumed that it was negative because the magnetic field made it go up. However, this is not the case, as we know with our modern understanding of physics, is that there's something called beta positive and beta negative decay. In this scenario, Rutherford only saw the beta negative decay, but later in this chapter we're also going to explore the beta positive decay that can happen in a nucleus. So before we move on to the next section, it's important to know the standard notation of how we write atoms of elements in notation like this. So it's similar to chemistry, what you do in there. And so let's say we have an atom of carbon 12. The way you would write that is you would have a carbon symbol, and beside it you'd have a 12, which is the atomic mass, and a 6, which denotes the number of protons in that element. So the mass number we know from chemistry is that we calculated it's the number of protons plus the number of neutrons. So in a question, if you were asked how many neutrons are in this atom, then you just subtract the atomic mass number from the number of protons, and you could get the number of neutrons from there. Now, there's also something that's really important to note here, is that there's something called isotopes, where the mass of a certain type of atom could vary depending on the number of neutrons that atom has. So we could have carbon 13-6, carbon 14-6, carbon 11-6, it doesn't matter. However, the number on the bottom, which is the number of protons, cannot change for the same type of element. So you can't just have carbon 14-5 or carbon 14-4 because that will be a new type of element. That won't be the same element that we're talking about in this scenario. So that's just something important to note for the next section of nuclear physics, because we're going to be using this a lot in the types of decay when we look at what subatomic particles actually get ejected out of the atom in the types of decay. So the first type of nuclear decay that I'm going to talk about is alpha decay. Now, the main reason an atom undergoes alpha decay is because the atom is actually unstable and it can't hold on to that many protons and neutrons together in the nucleus, because it requires the strong nuclear force to keep those protons and neutrons together. And so when an atom wants to become more stable and release some of those protons and neutrons, then it undergoes alpha decay and the atom ejects an alpha particle. Now, an alpha particle itself is the same thing as a helium atom, except we don't call it that because it's not naturally formed by fusion or fission. And so we call it an alpha particle because it came from the core of another atom that had more protons and neutrons. So if we were to write the equation for this decay, then we would see that, let's say an atom like polonium-212 decays into lead-208 and an alpha particle. Now, there's two key concepts that you're using in this decay. It's conservation of charge and conservation of nucleons. Conservation of charge deals with the positive and the negative. So you have the same amount of protons. The atomic number on both sides adds up to the same amount. So here we see it's 84, and here we see it's 84 as well. So the charge was conserved during this whole process. The other thing that has to be conserved is conservation of nucleons, which means the amount of protons and neutrons that were there before has to be the same as the amount of protons and neutrons that were in the equation after. So that is represented by the mass number here, and we see that this law was also followed in this decay because 208 and 4 is the same as 212. So this was also followed when we wrote out our reaction. If you look at these numbers on the top and the bottom, and let's say you write out an equation and they aren't matching, then you need to make sure that you go through the whole process again and make sure that both numbers, the top number and the bottom number, are the same on both sides, because there's a conservation law in this type of decay. So the next type of nuclear decay that we're going to look at is beta decay. And beta decay itself can be split into two components. One of them is negative beta decay and one of them is positive beta decay. Now, beta decay doesn't happen as the same reason as alpha decay happens. Alpha decay happens because there are so many protons and neutrons that the strong nuclear force can't hold them together anymore. So to become more stable, the atom ejects a helium atom. However, beta decay occurs because the balance of protons and neutrons in the nucleus is not clear. So there might be one extra proton or one extra neutron that may be disrupting the whole balance of the strong nuclear force. And so that's why many normal elements that aren't radioactive go through beta decay as well, such as carbon and magnesium. So first we're going to look at negative beta decay. And in this process, what happens is that a neutron becomes a proton, and in that process it ejects an electron and an antineutrino. Now, an antineutrino we'll look at later in chapter 17, which is the last unit of Physics 30, and we'll learn about the standard model of particles, because this is another type of elementary particle that has no mass or charge, but we still put it here because this happens in the process. And what this is related to is actually the spin of the particles inside the protons and neutrons. And spin is something we'll explore later in chapter 17 as well. All you have to know for right now is that this is the process in what happens, and that everything on the bottom and the top is balanced. That's all you need to know for this chapter right now. And then we can look at positive beta decay as well, in which a proton turns into a neutron, and in this process it ejects an electron. So here we see magnesium-23 turn into sodium-23 because one proton turns into a neutron, and to balance that charge, it emits a positron outside of the atom and a neutrino. And so these two decays we see, they also follow the mass-energy equivalence. Now what does that mean, you ask? That's Einstein's famous formula, E equals mc squared. Now, the reason why we have to look at this equivalence formula in any type of atomic physics is because we see here that this antineutrino and this neutrino here, they were both forged out of nothing. Now, people here may ask, well, where did it come from? What happened? Well, there's actually something called binding energy, and that energy is the amount of energy that's required to either pull apart subatomic particles out of the atom or stick them together. So here, if we actually looked at the masses specifically, so if we went all the way down to the kilograms and the grams and the nanograms, and we looked at the actual masses very, very specifically, then we would see that the components on this side have a slightly larger mass than the components on this side, because that mass was used to form the energy to form these two extra particles here. And that's why we have to look at here. In nuclear physics, energy and mass are interchangeable. So a piece of mass could suddenly turn completely 100% into energy, or energy could somehow come together to become mass. And that's something we're going to be using in the future formulas of this unit as well. Now, the last type of radioactive decay is actually gamma decay, and this is somewhat different than all of the other decays that happen because there's not actually a change in the amount of mass or the number of protons that are in this element, so the element stays the same, except the only thing that happens is a high energy photon in the gamma wavelength is ejected out of the nucleus because it's really excited. So typically what happens is after alpha decay happens or after beta decay happens, the nucleus is really excited. And again, we go back to this formula, E is equal to mc squared, Einstein's famous formula. And that shows us that because there's all this excess energy after the nucleus gets excited, it's also going to release a photon to make sure it gets back to that non-excited state. And this photon is one of the most penetrating photons and is actually harmful to humans because it can go through, because it has such a high frequency and a low wavelength, it can penetrate through many layers of steel and through skin. So this is actually a dangerous type of decay to humans. And so this is a very simple decay that you don't really need to do anything for. You just need to remember that there's a photon that's emitted. So that's going to be it for today's topic on radioactive decay, and next time I'll be covering half-life and chapter 17. Thank you.